Okay, so today's kind of block session has to do with what I kind of themed explanation questions. And so there are a lot of different types of questions where they'll be like state and explain the reasoning for this. And a lot of different concepts kind of um, are um, tested in this manner. And so before we even start talking about particular things, I do want to make one specific note about these general questions. And it's a note to yourself too. Is like anytime a table is referenced in the question, you should use values from that table to support your answer. There is a reason why the IB, again, like I said before, the IB's choice of words in all their questions is very, very deliberate. And so if they say using table 21, they expect in your answer for you to cite values from table 21. Or if they say using table 12, explain why, then your explanation should include values from that. That's the only way you can prove that you actually use that table. So less vagueness and less kind of generalizations and use actual values, using the periodic table, table 4, which is like the atomic radii one, explain why sulfur is smaller than phosphorus or something like that. And you want to actually cite the atomic radii values in your explanation. So if you're looking for full credit on those explanation questions, you definitely want to cite the values that are provided in there. Those HNMRs or those IR questions and things like that, cite the ranges or the specific values that are mentioned in there so to support your answer. And that's a better way to ensure that you get full credit than trying to be very vague and trying not to reference that stuff. So use that table to show the grader that you are following the instructions for the exam. Yes.
Is there a difference between like referencing XYZ versus using
No, I don't believe so. So, well, I guess, okay. I think sometimes when they say using, that's usually a calculation question. And when they say reference, that's usually an explanation question. I think that's when they say that. So like, they'll say using table 12, calculate the enthalpy of the reaction, but then they'll say, with reference to table 4, explain why the atomic radius it decreases as you go across and stuff like that. And so, yeah, so I don't think those terms are significantly different, but they're just used in different contexts. Yeah, that's a good question. Okay. So ideas that I wanted to kind of talk about here for state and explain. Okay. First one. Understanding the hydrogen emission spectrum. Okay, there's a variety of aspects of this that you have to understand and be able to explain on a paper 2 question. Okay, and so key ideas with this, okay, before you even start kind of illustrating and visualizing this is emission occurs when electrons return to return to a lower energy state after being excited. So higher energy level to lower energy level is an emission. Absorbance is the opposite. Okay, so with this, this is where the different lines of light are emitted from these jumps between energy levels here. Okay. You also want to say energy levels converge at higher energies. Okay. So therefore, the further and further you get away from the nucleus, the closer and closer the energy levels are from each other, and the smaller the difference between energies of those energy levels. Yeah. And that's supported kind of by the results of the hydrogen emission spectrum, because when they looked at the data here, this is kind of what the energy levels looks like in the data. And so you were able to observe that jump down from energy level 2 to 1 as an emission of UV light. And all the jumps down there, down to energy level 1, were UV because they exceeded the energy requirements for visible light, so they're all UV. Whereas jumps down to 2 were your visible spectrum because they were lesser amount of energy, and so therefore they were in the visible spectrum. And then infrared jumped down to the 3rd energy level. Okay, but you need to understand that no matter what jump you have from down to 2, it's always going to be less than the jump from 2 to 1. Like this jump here is going to be larger than any jump down to 2 because the energy levels are converging at such a high rate that that difference won't ever kind of be overcome. So you're not going to have some huge jump that emits UV light from a much higher energy level down to 2. And with these visible lights, you can also illustrate this in kind of a spectrum. And a spectrum projects lines of radiation or lines, the emission lines across this band. And you have high energy and then low energy. And if you're mapping out these lines in this kind of spectrum here, you're going to see that the low energy going up to higher energy, there will be an increase, but the increase will decrease as you go from low energy to high energy. So this might be 3 to 2, this might be 4 to 2, this might be 5 to 2, and then this might be 6 to 2. So that spectrum provides evidence that the energy levels converge at higher energies because the amount of energy that's increasing in each emission is decreasing.
Mr. Chong, I have a question.
Yeah.
So what do you call the lines that go from a lower energy level to higher energy level? Is that ionization energy?
Well, okay, specifically there's only one ionization energy. That's a good question. So eventually you get to a point where the energy level, is n equals infinity. So that's the very edge of the atom. And if an electron goes from the ground state to that infinite level, that's ionization energy. So all the other ones that are just jumping up to higher energies, that's just absorption. But for ionization energy to happen, it has to be from its ground state to n equals infinity, exactly to, not like past n equals infinity, but right to n equals infinity. That means the electron's being lost from the atom. Okay. Did that answer your question, Mira?
Yeah, that was it. Thank you.
Okay. You're welcome. So yeah, you may have to illustrate different electron movements on here, and ionization energy is one of those examples here. Okay. This is your spectrum here, and remember, low energy means low frequency and long wavelength. Okay, those three things, those three ideas are all related to each other.
Mr. Strong,
Yes.
did you say UV light has the highest energy, or what do you say?
UV emissions are the highest of the hydrogen emission spectrum in energy wise. Yes. But the lines I drew were just for the visible spectrum. Bless you. So like all these lines that drop down to n equals 1, those are the highest energy emissions that a hydrogen atom can release.
Mr. John,
Yes.
will the ground state always be n equals 1?
Yes, because we're dealing with hydrogen for all of these. So yes, n equals 1 should be the ground state.
So in this case, the color red would have the highest energy because it's the shortest wavelength.
No, red is the, wait, hold on a second. Red is the longest,
Oh, so it'd have
the lowest energy. Yeah.
Okay.
Yeah, so in case color wheel sketch, it's given to you in your data booklet, but on the multiple choice you won't have it. Roy G. Biv, and it goes this way from low energy to highest here around the circle until it gets to violet. So keep that in mind. Okay. Questions about that? Higher level state and explain. This is going to be colored compounds. Okay. Because understanding why transition metals form colored compounds is a kind of big explanation idea, because it incorporates a lot of different concepts that are required for the color to actually be transmitted by the species. Okay. So for the transition metal, you want to emphasize that it has a partially filled sublevel, D sublevel. Okay. Because what that allows to do is that allows electron movement between the split D sublevel. Because when ligands bond to it and form that complex, that compound or complex ion, I should say also, it splits the D sublevel, and that difference in energy is what colors get absorbed by that complex. And so that split D sublevel, the electrons jump up by absorbing energy from the light that's being shined on, that is being shined on it, shown, whatever. Okay. And so whatever's left is transmitted. And that's what you see. Okay. So this is where as well complementary colors come into play as well, because if you absorb violet, you're going to see yellow. If you absorb red, you're going to see green. And so there's no emittance happening here. The electrons are not giving off energy in that kind of concept as with the hydrogen emission spectrum. It's just absorbing certain frequencies of light and allowing other ones to pass through, and that's what you see. And so you want to emphasize, oh yes, Alex. Complementary color, correct. Yes. So transmitted complementary color. So the color across the color that's being absorbed from the color wheel. So it's kind of tricky because since you're transmitting the complementary color, you have to figure out what color is being absorbed to judge how far the gap is there. So like if you see yellow, that means it's absorbing violet, which is the highest energy, which means it has the largest gap that's occurring between the D sublevel. If you see green, that means you're absorbing red, which is the smallest gap, because this gap here is what tells us what kind of color is going to be absorbed. And so if you're absorbing violet, oh, that's not going to work. Okay. You'll see yellow. And that violet is the greatest split. Yeah, it has a couple of different factors. So that's what we're going to talk about next. And so understanding why the color varies because of the split D sublevel is the first kind of fundamental thing. But then you talk about, okay, what about the complex causes the change in color? And so there's kind of three major things. Let's see, factors that affect color. Okay, one, it's the element itself. Two, it's the charge of the element. And three, it's the ligand, what is being bonded to it. And you have a table in your data book that tells you what's the strongest ligand and what's the weakest ligand. And so those three factors combined kind of tell you, and based on the color that you see of the solution, how split the D sublevel is. A really common question will be I'm trying to word it right, but like the question I've seen before is like, state and explain why copper solutions are generally blue, right? And so if you're going to talk about that, you need to talk about, well, copper is a transition metal with a partially filled D sublevel. And so when it splits, it absorbs, well, if you're seeing blue, then it's going to absorb orange. So orange is complementary. So the split D sublevel absorbs orange frequencies of light, and so therefore the complementary color is transmitted, and that's blue. Okay. Well, yes, Alex. A stronger, wait, sorry, what'd you say? I didn't let you finish. The ligand? Yeah, a stronger ligand causes more repulsion, which causes the D sublevel to split further. Higher energy, yes. So the stronger the ligand, the more it splits, therefore the higher energy that's needed for the electron to jump to the other part of the D sublevel. Yes. No, I wouldn't. I would say that's like the last thing that you would really consider. Like I'd consider ligand and then the charge and then the metal itself. Yeah, because like I'm trying to think off the top of my head if there's a necessary trend. I don't think I would see the IB testing you about that kind of aspect of it. Okay. Questions about that? Okay. Back to everyone. Okay. Let's see, how do I want to do this? Okay. Let's talk physical properties. Okay. And physical properties are directly related to your IMFs, your intermolecular forces. You should never really say bonding when you're talking about physical properties like boiling point or like density or viscosity or surface tension or whatever. It's all about the attraction between the species. Now, in ionic or metallic bonding, is the IMF the same as its bonding? Yes. But in covalent molecules, it's not. And so you'll see kind of a difference there in how you kind of explain things. Okay. In the ionic bonding / the IMF of it, you have the electrostatic attraction between oppositely charged ions. Okay, so understanding ionic bonding does help you kind of understand the characteristics of ionic compounds and whether the melting point increases or decreases. To strengthen that electrostatic attraction between oppositely charged ions, you do two things about the ions. One, the charge of the ion dictates how strong that ionic lattice is. So a 2 plus is greater than a 1 plus. A 2 plus and a 2 minus is greater than a 3 plus and a 1 minus. Generally, you're doing the product of the two charges. And if those are all the same, then you use ionic radii as a tiebreaker. The smaller, the stronger the attraction. So if everything has the same charge, then you go, okay, which compound has the smallest ions? And then that will dictate your strength. And so if they're trying to say, state and explain why magnesium oxide has a higher melting point than sodium chloride, you would mostly address the fact that magnesium and oxygen both have a two positive and two negative charge respectively, versus a 1 positive and 1 negative charge, meaning that the larger the charge, the greater the ionic attraction, which therefore strengthens the attraction between the ions, which makes it more difficult for it to melt and to break those attractions.
Wait, but why is the 2 plus and 2 minus greater than 3 plus and 1 minus?
Because when you actually calculate this, which you're not going to have to do, Luthia, when you actually calculate it, you actually take the product of the two charges to figure out which one's stronger. So the product of this is 4, whereas the product of this is 3.
Okay.
Yeah. Okay. Metallic bonding / your IMFs here. We don't really call them IMFs because really intermolecular forces has to do with like molecules and stuff like that, and these aren't molecules, but I kind of want you to kind of think of this as forces of attraction here and just kind of be careful with it. Metallic bonding is your electrostatic attraction between positively charged ions and delocalized electrons. Right? So a metallic bond that happens with metals is between the metal ions that have given up its electrons to form a delocalized kind of network of electrons, and then the positive cations that are left over. And so with this, there are still two factors, and they're similar to ionic bonding. The charge of the metal is the first factor. So the higher the charge, the stronger the bonding. And then if they have the same charge, then you go by ionic radii. The smaller it is, the stronger it is. So this is how you identify like what's the strongest metallic bond available in different substances. So they might say like sodium, like magnesium, potassium, and lithium. Well, magnesium having a 2 plus charge automatically trumps any of the group 1 metals.
And do you first look at the charge or do you look at both
look at the
things?
charge first. You look at the charge first.
So if the charge is higher, you don't have to look at the ionic radii.
Correct.
Okay.
Yeah. Questions about that? Okay. Simple covalent molecules is where we get into the real kind of IMFs and what we consider intermolecular forces of attraction with these molecules. And I say simple covalent molecules, meaning that they're independent molecules, not like diamond or SiO2, where it's a giant network and everything's covalently bonded. We're talking about I'm able to take one molecule of the species and separate it from all the other molecules if I wanted to. Like I can take a water molecule out of a sample and I can take a CO2 molecule out of the air. Those are simple covalent molecules. And so with that, now you've got 3 different types of attractions that you have to talk about. London dispersion forces, dipole-dipole, and hydrogen bonding. Okay. Now, another term for these 2 forces combined are van der Waals forces. So London dispersion forces and dipole-dipole are grouped together under the umbrella of van der Waals forces. Some old IB tests might treat London dispersion and van der Waals as the same thing, but the new curriculum really explicitly says that van der Waals forces includes dipole-dipole as well. So London dispersion forces happen in all molecules, but they're the strongest in nonpolar molecules. Molecules that have some form of symmetry or the same terminal atoms completely around the outside. Dipole-dipole happens in polar molecules. So any molecule that has somewhat of polarity, there is dipole-dipole existing. And hydrogen bonding happens when there's H bonded to N, H bonded to O, or H bonded to F in the structure. Because what that does, because those are the 3 most electronegative and smallest elements on the periodic table that can bond, they create a very, very distinct separation of positive and negative charge attraction between that bond. And that positive is very, very great, and it's almost like an ionic attraction. So it's a very, very strong attraction compared to the other ones. So when you have to make sure you draw out structures, because the IB's savvy enough to ask you which of the following has hydrogen bonding, and they'll have N, O, or F in every single structure. Like they're savvy enough to understand that some students just memorize if you see N, O, or F, there's a hydrogen bonding, when in reality, when you draw the actual structure, there is no hydrogen bonding. You know, you'll see things like CH3O, CH3, or like CH3, CO, CH3, or something like that. Okay, when you draw these out, you find that the hydrogen's never actually bonded to the oxygen. And so there isn't hydrogen bonding in those cases. So make sure you draw the structures out to make sure that there is actually hydrogen bonding exhibited in here. Actually, you know what? I'll move this around a little bit.
Mr. Trong,
Yes.
so if one of like an example, it had like NH3 instead of a CH3, would that be hydrogen bonding?
Yes. So if you had something like probably NH2, but yes. So like this with that, hydrogen bonding, yes. So if you see an NH2 group or something like that, or an NH group even, yes, there's going to definitely be hydrogen bonding there.
Okay.
And you also want to make a note, I should say this as well, is that the hydroxyl group is weaker than the carboxyl group when it comes to force of attraction. What? Yeah. So because remember, the strength of the hydrogen bonding is how positive that H is. Well, when you have a carboxylic acid, you not only have one O pulling electrons away from it, but this whole region here is pulling electrons away from that hydrogen. So that hydrogen is going to even be more positive than in an alcohol, which is why these become acids, because the H is so positive that the molecule would rather donate it to something else than to keep it. And so that's why those carboxylic acids kind of behave that way, because it's so polar, it's stronger than your hydroxyl. So that's kind of your tiebreaker here. Generally, when you compare these, the IB tries to keep the molar masses fairly similar, right? Because the strength of London dispersion forces, if you have a massive enough molecule, it's going to be quote unquote stronger than a hydrogen bonding, right? So oftentimes when you compare these, you'll see them be similar molar masses, so that way the mass doesn't affect your comparison here. And so because once it comes down to it, if they both have like dipole-dipole, London dispersion forces are the tiebreaker, and those London dispersion forces are kind of based on mass. This is why I2 is a solid, and then bromine is a liquid, and then chlorine and fluorine are gases. Because the increase in mass means the electrons are more mobile, and it creates more of those dipole moments, those temporary dipole moments that strengthen those LDFs. But it's really your job to state and explain is to talk about identifying what type of IMFs are in each covalent molecule and which ones are stronger and what strength has to do with it, right? So, for example, for boiling point, stronger IMF means stronger attraction, which means more heat / energy needed to break the IMF. And you want to talk about all these things in your explanation question, because nothing is inferred. Everything has to be explicitly written on your paper. So you can't just assume that they know what you mean. And so you need to be very explicit about explaining these points here. I'll let me scroll up a little bit. Questions so far? Nathan? Okay, one last thing and then we'll take a break. One of the state and explain things that I've noticed that they kind of have started, well, maybe not they started, but I've noticed on the questions is what they'll do is they'll talk about bond strength, bond length, in terms of bonding here. And this is useful because it kind of helps you explain kind of understanding what bonding is, and then it also requires you to draw Lewis structures to kind of understand the bonding itself. And I'll put bond order in here as well, because I think bond order is what you kind of want to use to explain your rationale. And so they'll say things like C2H4 versus C2H6, or CO2 versus CO3 2 minus. Or like C6H6 versus C2H4. And so they're incorporating a couple different things here. They're incorporating resonance on some of these. They're incorporating Lewis structures, and then they're incorporating if you can interpret the bonds strengths in these structures. And so C2H4 is a fairly straightforward one. And with all these organic compounds, to be honest with you, with these C2s, the CH hydrocarbon compounds, essentially you kind of distribute the hydrogens evenly around the carbons, and whatever bonds are left, they have in between the carbon, right? So when you see C2H4 and you have two H's on each one, and you're like, okay, each carbon's missing a bond, that means I need to add a bond here. So those are fairly straightforward. If we're comparing bond strength between this, the double bond is a stronger bond, which means a shorter bond length. And you would cite, well, C2H4 has a double bond, C2H6 has a single CC bond, and a double bond is stronger than a single bond, so therefore the bond length will be shorter because of a greater attraction between the two carbons. CO2, excuse me, CO2 versus CO3 minus is kind of a tricky one because CO2 looks like this and CO3 is resonance. Make sure you're writing the brackets. Hopefully your brackets look nicer than mine do. But the brackets and the charge around these polyatomic ions. And so when you look at this, actually, you know what? The C to O bonds, here, there's 4 bonds for 2 locations. So your bond order is 2. Here, it's 4 bonds for 3 locations, so it's 1.33. So what you could say is that the double bond, the bond length in CO2 is shorter than the bond length in CO3 minus because CO2 has a bond order of 2 and CO3 minus has a bond order of 1.33, which means it's a weaker bond. It essentially represents 1 1/3 of a bond versus a double bond. Okay. So using those ideas and those concepts to explain bond strength and bond length and using bond order is something that they could also ask you about to kind of emphasize that.
Mr. Chong, did you say CO2 would be the stronger one?
Yes. The C to O bond in CO2 would be stronger than the C to O bond in carbonate. Yes, Maurice.
These are stronger because there's less shared electrons over the same, or over like more, or like the same amount of shared electrons over the same amount of electrostatic interaction on individual electrons.
Yeah, I guess that's a qualitative way of saying the bond order in numerical ways. Yeah, I could see that. Yeah, so you're saying, yeah, there's 3 domains versus 2 domains with the same number of electrons, and so there's a weaker attraction between the carbon oxygens. Yeah, I can see that. Okay. Questions? Okay. Oh, yes, Alexander, sorry. Sure. Bond order is a calculation that we use to essentially calculate what that bond is worth. And so you take the number of total bonds between the 2 elements and divide it by the number of regions those bonds occur. And so a bond order of 2 means that each of the bonds represents essentially a double bond. And a bond order of 1.33 means that it essentially represents a bond and a third. So it's stronger than a single bond, but not as strong as a double bond. So it's somewhere in the middle of that. Does that make sense? Yes. Okay. Let's take a 5 to 7 minute break. We'll resume at 9:05. You should hear the bell sound off in the classroom if you're on the Zoom, and we'll get started again then. So I'm going to pause the recording right now. So back from break now. What we're talking about here is reaction rate and collision theory, because this seems to be a kind of a conceptual thing that they like asking about. And the 2 main ideas for collision theory are you want correct orientation and the correct energy for the reaction to occur. Those are your two main ideas. And so everything that affects the factor, everything that's a factor that affects rate of reaction affects one or both of these ideals to speed up the reaction. Okay. And so when you group things like concentration, surface area, nature of reactants, and pressure only for gases, all of these techniques are designed to increase the frequency of collisions. Because if you increase the frequency of collisions, you increase the frequency of correct orientation. Just by default, the more collisions you have per second, the more of those collisions could be the correct orientation per second. So that's how that speeds up the reaction. Temperature does two things, okay? It increases the energy of the particles so that more particles have the correct amount of energy to react, and it also increases the frequency of collisions due to the fact that the particles are moving faster. So faster moving particles, more frequent collisions as well. But the idea is that the increase in energy of the particles is more influential in the rate of reaction versus the frequency of collisions. Because you can have as many collisions as you want. If they don't have the right energy, then nothing's going to happen. So making more particles have the right amount of energy to react is kind of vital to this rate of reaction here. Yes.
One's in purple, just like increase the reaction.
All of these increase reaction rate.
But the temperature is also you get more hydrogen.
No, not necessarily. Because that's Le Chatelier's principle. It depends on whether it's endothermic or exothermic. Yeah. So these are all, in this context, it's just, they all speed up reaction. A catalyst lowers the activation energy. Therefore, more particles have the right amount of energy. Let's write lowers activation energy by providing an alternate pathway. It's really strange that they don't say alternate pathway like in like their syllabus tracker, but that was on the mark scheme. So lowers activation energy by providing an alternate pathway for the reaction to occur. Yes.
Is this where that word adsorption?
Yeah, adsorption is a catalyst that's like a solid, which the particles will adsorb onto the surface of it to allow it to like react more easily. Because when particles adsorb to the metal, they increase the likelihood of correct orientation because the part that's hanging up is always the correct orientation. So then when particles collide with it, you've ensured correct orientation. So they're more likely to react. Yeah. Like when you hydrogenate like alkenes, like by adding hydrogen, you usually use a nickel catalyst, which adsorbs the alkene, which then allows the hydrogen to attack it from the right direction so that it will react. So it speeds up the process. Yeah.
Mr. Chong,
Yes.
why is there a star next to increases the energy of particles?
Because of the two reasons why temperature affects reaction rate, this is the more important one, Erica.
Okay.
Yeah. So like they'll ask like state and explain why temperature increases the rate of reaction in terms of collision theory. So you'd say both, and then they might say identify which factor is more significant. Yes.
Any exceptions in any of that?
Wait, what do you mean exceptions? Like the conditions? That's in topic 1. But so remember, for ideal conditions, you want to have the particles as far away from each other, moving as quickly as possible, so there's less interaction with each other, and you want as much space as possible. So to diverge from that, you would want high pressure and low temperature, because then the particles would be more interacting with each other, and the volume would be more significantly impacted by the particles and everything like that. And so, yeah, I think that's what you're asking about, right? So gases deviate away from ideal gas when there's high pressure and low temperature. Yeah. We will talk about equilibrium more in 5th period, but just in case people can't get there. Talking about the equilibrium constant. K. And the reaction quotient. Q. Okay. We talked about this in compare and contrast video a little bit about how you solve for them the same way, but they are telling you different pieces of information. And this is also in the explanation and things like that. And you want to emphasize a few things when you're kind of talking about this, okay? 1, temperature is the only thing to change K. So the only thing that can affect the value of K is temperature, because heat causes a shift in the reaction, but since heat is not in the actual expression, it causes a shift that cannot be essentially balanced, because it's not actually part of the species that are reacting. So it kind of tips the scales in one way, but doesn't allow you to be able to kind of balance things back out. And when you talk about, so that's the K value. The position of equilibrium is essentially just how it shifts. So when you increase or decrease something, how does the position of equilibrium change? Does it shift to the right? Does it shift to the left? Is there no shift? That is all kind of applied in here. And you compare K versus 1. So the value of 1 tells you what's favored, products or reactants. The reaction quotient identifies where the reaction is in relation to equilibrium. So Q is non-equilibrium calculation of the same value, and it tells you it kind of gives you an idea of what do you have to do to shift to reach equilibrium. So Q you compare to K. Okay. If Q is equal to K, then you're at equilibrium, and there's nothing to worry about, because there's no shift that's going to occur because you're already at equilibrium. It's when you have Q is greater than K or less than K that you have to cause a shift, a position of equilibrium shift, so that you can reach equilibrium. If Q is greater than K, you have too much products. So it has to shift to the left to reach equilibrium. If Q is less than K, you have too much reactants. And so you're gonna have to shift to the right. So you're not at equilibrium yet. You have to do some movement to reach equilibrium here. Questions about that? Okay. I'm actually going to go out of order and go back to trends here because I was thinking about this more and I kind of want to emphasize this state and explain because trends is a very kind of common thing as well that you want to kind of discuss. And so we're going to look at trends here. And like in review sessions, like I've emphasized before, there's only two things that really affect a trend when you're looking at a periodic table as you're going across the period or down a group. And these are the main ideas you want to focus on. As you go across a period, the idea is you have the same energy levels. Okay, that's what's similar. What's different is you have more protons, which we say is a higher effective nuclear charge. Okay. And so that effective nuclear charge increases the attraction which then can be applied to whatever trends that you're doing, ionization energy, atomic radii, electronegativity. That increased attraction helps you explain the reasoning for that. As you go down a group, the idea is you have the same effective nuclear charge, because essentially the number of protons pulling on the outermost electrons is the same. Whether it's lithium, potassium, or sodium, they have one proton pulling on one valence electron. So that's the same effective nuclear charge, but what's different is additional energy levels, which means more shielding of attraction. Oh my gosh. And they are further from the nucleus. And so that all adds up to weaker attraction. Okay. So no matter what trend you're really talking about, other than maybe ionic radii, which isn't really a trend in the context of what we're talking about here, whether it's atomic radius, ionization energy, electron affinity, electronegativity, all of them can be explained with these two major ideas. And then you apply them to each trend as needed for this. Those are your explanations. Now, the tricky thing is that there are exceptions to this trend rule. And you'll notice in some of these trends, there are dips when there should be increases and things like that. And I say whenever you have to try to explain an exception, you need to refer to the, yeah. Wait, what? Oh, okay. Oh, sorry. The orbital diagram. Okay. Knowing where the location of each of the electrons are in the different orbitals, because the exceptions are usually due to electron-electron repulsion. So those exceptions usually have to do with, okay, if I'm losing an electron here, do I benefit by minimizing my repulsion? Am I making it a more stable species? And so if you ever have an exception to a trend, draw out the orbital diagrams for each of them, because that will usually illuminate why they're different. Like when nitrogen and oxygen have an exception with ionization energy. Well, the last group of nitrogen and oxygen is 2p3 versus 2p4. And what you have to understand is that losing this electron minimizes repulsion in the oxygen. So therefore, it takes less energy to lose that electron because the oxygen will be in a much lower energy state if it loses that electron. Whereas nitrogen is already in a low energy state, and losing that electron would actually make it in a more unbalanced state. And so this is why oxygen is going to have a slightly lower ionization energy than nitrogen, because losing that electron actually lowers oxygen state because it minimizes the electron-electron repulsion, because now you have one electron in each orbital spinning the same direction to minimize, spinning in directions to minimize the repulsion. Whenever you add one to an extra orbital, a second one to an orbital, it creates an imbalance there. And that imbalance is only counteracted when you fill up the entire orbital. So anytime you have like partially filled sublevel, unless it's half filled, it's very unstable. So if you need to state and explain exceptions, always use orbital diagrams. That will usually tell you what's the issue here. Questions about that? I think I had something else. Higher level. So SL, take a mental break right now. State and explain how you would form a buffer, okay? And I know a lot of y'all hate buffers, so that's okay. But the idea with buffer solution is, here's what you need to understand about buffer solution, and hopefully that will help you understand how you make them. A buffer solution needs to have a conjugate acid-base pair that is weak in the solution. So when you have that conjugate acid-base pair acts as the buffer, absorbing OH minus or H plus. But so to make a buffer, you have to have a conjugate acid-base pair. And I think a lot of students think because it's called acid-base that it has to start with an acid and have a conjugate base. That's not true. They just picked one direction to say it, and you could have a base with its conjugate acid and still be okay. So don't be thrown off by the order in which the words are written in this description. And so the idea is you need to have a buffer solution that has a weak acid and a weak base. And a weak acid makes a weak base, and a weak base makes a weak acid. So if HF is a weak acid, okay, what else do you need in the solution to make a buffer solution? What do you need in the buffer solution? What else do you need in this buffer solution to make a buffer? F minus. Because F minus is the conjugate base of HF. So these can work in tandem to act as a buffer. Because HF will absorb any OH minus to make the conjugate, and F minus will absorb NaH plus to make HF. So they're working in tandem with each other to maintain the balance of pH to resist the pH change in the solution. And there's two ways to get that conjugate base. You could simply add a salt that has it, like KF, NaF, something that dissolves in water that generates F minus, or, bless you, you could add a strong base. Because when you add a strong base to a weak acid, it neutralizes it and creates the conjugate base salt. It essentially creates a salt that you would use if you had it available. But with this one, you have to be careful because you have to have the amount of OH minus is less than your HF, okay? So you can't neutralize all of your HF with OH minus. So you have to have some HF left and you have to have some F minus present. The only tricky thing I think they might do with this is like they might change the molar ratio from 1 to 1 to like 2 to 1 or something like that. So maybe they make the weak acid like H2CO3 and then they give you the same moles of OH minus and H2CO3, but that still works because H2CO3 has 2 H pluses that it can lose. So like the molar ratio is you could have twice as much base and still have a buffer solution. So like that's where I think it might be tricky, where they might say, well, H2CO3 is a weak base acid, and if I add NaOH to it, it takes 2 NaOHs. So the amount of NaOH that I could add to H2CO3 could be more than I would expect. So that's the only kind of tricky part there. Okay. NH3, weak base, ammonia. Okay. For it to act as a buffer, what other species do you need in this buffer solution? Alexander? NH4 plus. Careful with the plus. You got to write the plus because it's got to gain a hydrogen. And this has got to lose a hydrogen because you're making the conjugate. So this is your conjugate acid. And you can make that one of two ways. You could add a salt that has NH4 in it already, like NH4 NO3 or like NH4Cl. Or you can add a strong acid like HCl to generate some of that NH4 plus. And again, NH3 and NH4 work in tandem to create each other. And that's how that buffer solution works, because it's able to absorb the H plus and the OH minus into its conjugate system. Therefore, it's no longer freely roaming to affect the pH. Questions about that?
Mr. Charles,
Yes.
what if they work in tandem to produce each other to maintain a pH? Is that what?
To resist a pH change. I think the word resist is kind of a key word here, Erica. So, because the pH will change a little bit, but it won't change as much as if there wasn't a buffer in the solution.
Okay.
So I think the key word here is resist pH change.
Okay, thank you.
You're welcome. Okay. Redox reactions, electrochemistry. Okay. I think a lot of students were still struggling with the idea of oxidizing and reducing agents, right? And so you've got to remember that the oxidizing agent is the one being reduced. Because the fact that it's reduced causes something else to oxidize. And then the reducing agent is being oxidized. And usually on this type of question, when you only have a coin flip, to get the full mark, you have to explain why. And so here you're going to probably have to apply a definition of redox. And so they'll say in the question, in terms of hydrogen oxygen change, or in terms of electron transfer, or in terms of oxidation number, state and explain why MnO2 is an oxidizing agent or reducing agent. So it's not enough to say, oh, it's a reducing agent. You have to say, well, the Mn goes from Mn2 plus or plus 4 here to Mn plus 7 in this species. And so you have to cite values here. You have to make sure you explain it completely to discuss that. So understand that and make sure that usually it's oxidation numbers that you want to use to identify that. I gotta pick and choose here. Okay. State and explain. Bromine water. Okay. Bromine water is used to differentiate between alkanes and alkenes. Okay. And understanding how the reactions work is really kind of vital to this concept. And so with alkanes, for the bromine water to work, you must require UV light because you need the bromine free radical to work. Okay. An alkene requires no light because that C double bond is very reactive and it undergoes addition reaction. Because a double bond is very unnecessary for a structure, so it seeks to bond with other species, and that's why when the BR2 is available, the double bond will bond with the BR, and then the other BR will attack it as well. And so understanding why they're different allows you to understand how you use it to differentiate. And so the alkane undergoes free radical substitution. The alkene undergoes electrophilic addition. Questions about that? Okay. Our friend benzene. Okay. Now, a couple of things about benzene that, because I've seen a lot of kids ask certain questions, so I do want to address it with everyone to make sure. Okay. Yes, we draw benzene like this for simplicity's sake, but you need to understand all bonds are identical. They have delocalized double bonds. So really, there's not alternating single and double bonds. It's delocalized double bonds, meaning that every bond is the same. meaning the bond lengths are the same, the bond strengths are the same, and that resonant structure provides stability. Okay. Okay. And so this is why it doesn't undergo electrophilic addition like alkenes, because benzene is so stable there. If you were to disrupt the double bond delocalization by removing one of those double bonds, it would upset the structure too significantly. So you'll never see something like this, like an addition reaction that you would normally see for an alkene because of the lack of stability. But you can see a substitution reaction. Now for SL, you just have to know that that's a substitution reaction, that you're replacing an H with an NO2. HL, you know this as the nitration of benzene. And you will hopefully know all the arrows and diagrams that are involved in it because the IB loves this reaction. I'm trying to think, like, I feel like if you've done a lot of the paper twos recently, like of the recent exams, it almost shows up in almost every exam because it's a new piece of material that they like testing on it. It justifies their addition of benzene emphasis in their new curriculum. And so you'll see a lot of benzene in there, whether it's a outline the mechanism using curly arrows to show the nitration of benzene, or outline the species that are needed to reduce nitrobenzene to phenylamine. Those kind of key things are things that they like to ask about a lot. Might be a multiple choice question. It might be a short answer question. Oh, something I've had a lot of kids ask about. This is not necessarily a standard explain, but I just wanted to kind of address here. Addition polymers. There seem to be kind of a few multiple choice questions or even short answer questions kind of giving you an addition polymer and asking you to identify the monomer and stuff like that. And I think I want to make sure that students kind of understand, one, how polymers are written, and two, especially for the addition polymers, how you tell what it came from. A polymer is written in its repeating unit form. And so you might see something like this. But you have to understand that what that's saying and what that's implying is that there's another one here and there's another one here connected to it. And so understand that, because just because they give you a snippet of it, you have to understand that that part is connected on the other end as well. And so that kind of continually goes on for whatever length of the polymer there is. When you look at an addition polymer and you look at the repeating unit, all you really have to do is this. It's actually really easy. You remove the single bonds and you add a double bond here. So essentially all you do is you replace the bonds that are going out left and right with the double bond. And that's your monomer. That's all you have to do. Because all that happens in addition polymer is the double bond becomes the link between all the monomers. That's all it does. It's just a chain reaction. So there's no complicated part about it. Everything that's hanging off the polymer hangs off the double bond just the same in the monomer as well. So don't overthink that and just add a double bond between the two carbons that are in the polymer chain, and that's your monomer. That's the only thing that differs.
So, Mr. Chong, is everything inside that parentheses essentially just one unit?
Yes, that is the repeating unit.
Okay.
Now, oftentimes, Mira, when they have you draw it, they'll have you draw 3 repeating units, where you would draw the whole thing I drew here and then put parentheses on the outside of each of them. But I see multiple choice questions where they show you 1 repeating unit, so that could be that. Or they might do.
So if you're
if-
given 3, you would draw 3 separate parentheses?
No, you draw it like this.
Oh, okay, got it.
Yeah. So you just have to draw 3 repeating units and then parentheses on both sides of that set of repeating units.
This seems like a stupid question, but if we like forget the N, would that be bad?
If they're having you draw the polymer, yes. Sorry, sorry to bring it to you, Anna, but I would say if they're asking you to draw the polymer, that N is really important because that shows that you understand that it goes on, that keeps repeating on and on for N number of cycles. I had something in my head, now I've just lost. The hell's going on? Okay. Let's stop there. A lot of statement explanations there. If I think of anything else, then I'll add it on to the what the Trong questions tomorrow. But so we're going to end about a few minutes early. But again, if you want to stay on the call and ask questions, or if you're in the classroom and you want to ask questions, I'm more than happy to do that. I will upload this video soon.